going to talk about is what our future is going to be like. And what I want to start with is a quote from a good, close collaborator of Abraham Lincoln, Henry C. Carey. So he said, "Two systems are before the world. One looks to pauperism, ignorance, depopulation, and barbarism. The other to increasing wealth, comfort, intelligence, combination of action, and civilization. One looks toward universal war, the other to universal peace. One is the English system. The other we may be proud to call the American system, for it is the only one ever devised, the tendency of which was that of elevating while equalizing the condition of man throughout the world. Such is the true mission of the people of these United States, to raise the value of labor throughout the world, to improve the political condition of man, to diffuse intelligence and to promote the cause of morality, and to substitute true Christianity for the detestable system known as the Malthusian, proving to the world that it is population that makes the food come from the rich soils, and food tends to increase more rapidly than population, thus vindicating the policy of God to man." So this was Carey, and I want to emphasize what he said. He said the American system is the only one ever devised, the tendency of which was that of elevating while equalizing the condition of man throughout the world. And that is exactly the fight that we're engaged in today. And that's exactly the fight which is being played out in this opening salvo that we see from the BRICS summit and what's now emerging as a new development bank for the world, and you see people joining it, hopefully by the day. Now, it's this fight with which Lyndon LaRouche has spent his entire life being engaged in. And when we talk about the American system today, we're talking about Lyndon LaRouche. There is nobody left in the United States that embodies the knowledge that's been passed down to us from Alexander Hamilton, Carey, Lincoln, Franklin Roosevelt. It's embodied in LaRouche, who's not only built his own, has built upon the works of these great people who have come before him, but has also spent the past 50 or more years of his life advancing the science of the American system of economics, contributing more advanced insights into the actual science behind human economic growth, human population growth, deepening the knowable scientific basis behind the true science of economics that we now see the potential for finally propagating throughout the world. So that is that's really what we're looking at now when you see all these emerging world leaders, Christina D. Kirchner, Putin, Modi in India, and these people that are now courageously leading the charge against the imperial system. Of those people, Lynn and our organization, therefore, in the United States, play an absolutely unique role in having true insight into the nature of the human species. And that is what's behind Lynn's intervention over the recent period. As these developments from the BRICS summit and others have been emerging, Lynn has been making a very forceful intervention on the issue of what this new world system must be consciously based on. And we saw that first a few weeks back in his 4 laws that he put out, his 4 laws document, where he was listing the steps that must be taken inside the United States to ensure the survival of the United States in the world. And those were, following the impeachment of Obama, those were the implementation of Glass-Steagall, the elimination of the Wall Street system debt, the elimination of these fraudulent claims, reestablishment of a national banking system. Within that, the utterance of credit to productive projects, and then finally, and this is what I want to focus on today, a fusion driver program. That all of this has to be organized from the top down by our intention for a fusion driver program for the economy. So we'll get a little bit today into what that means. Now, the other thing I wanted to raise from LaRouche directly was, as a follow-on to the 4 laws, or you could say a development upon some of the aspects of his 4 laws, he's made an intervention over the past week or 2 on specifically on the issue of value and determining value. And it clearly comes up when we're talking about the fight with Argentina. And his response in this is there's no value in these claims of the vulture funds. Wall Street, there's nothing there. There's no value in the idea, or take the idea of a price being set by some kind of statistical average of the markets, or a price of something being set by what people are willing to pay for it, the power to sell. There's no value in this. So he said a few things, which I just want to communicate. He said, when you're talking about the issue of values, he said you have to start with what are the needs of society. That's the basis for defining everything. That's your standard. Then you can go to fundamentals, material fundamentals. He said we need a new decision to replace the failed system. We need a new standard of international value as the basis of that system. And then he said, look, you have to take a step back to prepare for a thrust forward. Ask the question, what is physical? What is physical in terms of the productive powers of labor? We have to get people together to argue this through. We need a list of what are the things that mankind needs to produce inside the solar system. There are things that must be produced for the base of productivity. We should get a list of them and define a set of areas of interrelation. Energy flux density is the scientific principle of the basis of a scientific view of economy. And so he said, work on getting together a new bill of materials. Or what is humanity going to need? Make a new bill of materials. Not a selection. Get everything that you need to produce. Get everything that you need to produce everything that you never thought you could produce. And then it goes on, but he then threw out, he said, you have to define what are the requirements of the solar system. What's the bill of materials to run the solar system? Now just yesterday, he came down in discussion with the basement team and said, I'll just read a little short thing from what he said there. He said, what we need is a high energy flux density program. We need productivity increases. That's what's needed. We need actual creativity per se. We need to increase above all else the physical productive powers of society. We have to go to higher levels than have ever been achieved before. The reality is, can you make something happen which has not happened before? That is the only truth. Now, this is clearly a fundamentally different conception of value than what predominates today, than what's rattling around the minds, not only of the Wall Street guys, but then is rattling around the minds of the American citizen. And it flies completely in the face of this Wall Street notion, which has been imposed on the population to keep them quiet, to keep people pessimistic. And it has everything to do with what it is that makes mankind a unique species in the universe. The fact that man is not a fixed species, right? You look at the biosphere and you look at animal and plant life over time, and you see the unique role that each species of organisms plays in terms of what kind of chemical compounds does it produce and add to the biosphere, what kinds of materials does it interact with, what kinds of energies does it interact with. For example, you take plants, which are able to absorb sunlight and interact with solar radiation. They produce unique chemicals that didn't exist before chlorophyll and photosynthesis existed. And then they add those, the chemicals and the materials that they've changed, they add that to the biosphere. That then becomes a part of the structure of the earth. Now, animals are fixed in what they do. Not that there's not change over time, right? When you look back 1 million years ago and you look at the kind of living processes on Earth and then today, you have change over time, but it takes tens, hundreds of thousands of years for the turnover of species through a process of evolution. Now you look at man. Man is not fixed. The kinds of changes that you see between an evolutionary process of life in the biosphere, the kind of change of the types of chemicals produced, access to different parts of the biosphere, man is able to make these kinds of transformations within one generation. And we do that through more advanced technologies, which are the result of discoveries. Now, the way that this is expressed, or one primary way that this is expressed, is through the economic indicator of increases in energy flux density. And people may or may not be familiar with the concept, but the idea of energy flux density is the question of the density of power that can be wielded by one individual of the species to cause change. And we'll get a little bit into some specific examples when we talk about fission and fusion. But if we look over time, now what this is a chart of the the power density per capita within the United States from 1780 up through today. And if you look at this, you notice a few things. You notice that over time, the power consumed, power wielded per capita, and then when we say power per capita, what we're talking about here is not just, how much electricity, how big was your electricity bill this week. But what you're talking about is how much power is involved in actually sustaining and running society. From your industrial power, the power required for transportation, the power required to meet all the needs of society, divided up per capita. And now if we look over time, we notice the obvious trend that this has been increasing exponentially. The amount of power behind each individual in society has been increasing exponentially. Now this throughout the existence of the United States. If we did a study of all of mankind, we would see the same thing. That the power wielded behind each human individual over time has gone through an exponential increase. Now we notice something else, and that's involved in these different colors here, is that it's not always been the same power source throughout time. Man has gone through a transformation in the primary source of power to run society. So you see, starting from the beginning of the United States and going back long before that, the primary source of power for man was wood, right? We burned wood for everything, for heat, for power in industries, and so forth. Now, around the middle of the 19th century, you began to have coal take over as the primary power source. Due to what? Due to the discoveries involving things like the the steam engine, right? Then, around the turn of the 20th century and a little bit later, the early part of the 20th century, you have the dominance of petrochemicals and natural gas, which is obviously the primary, that and coal are still the primary power sources in the United States today. Now, notice something, around 1970, you have a new power source enter, nuclear fission. Now what do people notice? Rather than the introduction of the new power source resulting in the tapering off of the old one, right? And then the raising of all of society to a new level, something happens in 1970. And that's that this completely levels off. There's been no growth in the amount of power consumed per capita in the United States since 1970. And if you see now, since about 2000, it's begun to fall. So we're actually declining in the amount of power behind each individual in the economy. The entire thing is beginning to collapse. Now what should have happened is that nuclear fission should have taken over and taken us approximately doubled the amount of power per capita. And then probably around the turn of the 21st century, we would have seen the introduction of nuclear fusion. So we should have already been living through a decade approximately of being a nuclear fusion economy. Yes?
How do you get the steepness of that curve between 70 and 2010? How do you extrapolate that curve?
Yeah, well, this particular chart is just a basic extrapolation of the general exponential curve. But then the interesting thing, I don't have a picture of it now, but there were actually projections done first by the Kennedy administration. Under Kennedy, there were projections done for power per capita by the year 2000, and that put us somewhere in the range of 20 to 25,000. But then LaRouche's organization, EIR, did economic studies in the 1980s, and they actually projected that with the breakthroughs, the technological breakthroughs that would have come with the SDI, if we had applied those right away, we could easily be at 30,000 today.
Sorry about that.
Yeah.
You wrote an article on us how the funding was pulled from fusion.
Yeah.
And Jason made some comments a week ago, 2 weeks ago, that had the program, how much we're actually owed as a population, because our lives have not developed to the extent that they should have, had we not pulled the funding on fusion. And the way I feel about it is we're owed money. We're owed something.
If we're owed a lot, there would have been a lot more people in the country. No, I'll get into some of that actually. Okay, so this tendency, which goes completely against the greenie ideology that came in around 1970, right? And that's not a coincidence. This tendency for man to actually increase what's required to sustain life, right? But it also implies an increase in each individual's power to cause change. This is natural. This is the natural tendency of human beings, right? LaRouche has identified it as a conscious science now, but the human species has been doing this for millions of years. So this is what human beings are, this is a reflection of what human beings are supposed to do. So what I want to talk about today is that last little tiny dark gray section here, right, of fusion. I want to talk a little bit today about fusion, yes?
Do we have fusion nuclear power now?
We have fission power plants, we do not have fusion power plants.
Okay, so are fusion power plants dangerous?
Mm-mm.
Okay, so it's all a hoax?
No.
Chernobyl was a hoax and Fukushima was a hoax?
The scare around fission was a hoax. I'm going to get in a little bit into why we don't have fusion power plants today, so hopefully it'll be clearer by the end. So, so I want to get into fusion. And as LaRouche said, the pursuit of fusion must define the mission orientation of nations of the world, and it must define how we set values in this new emerging system. And he's called for an international conference on value. He said, look, we have to convene a conference, we have to get nations together to discuss the mission orientation around thermonuclear fusion and pursuit of space. And we've got to define everything else in that context, including all of the currency and other values have to be set from that context. So, let me get a little bit into just touching on what some of this is. Fusion, fission, nuclear processes. What are we talking about? The basis of fusion, or the idea of fusion, was actually born at the end of the 19th century. And by the end of the 19th century, man was operating within the domain of simple chemical processes. So what I mean by that is man's economy, man's scientific power was based on our ability to generate new chemical compounds, to cause new kinds of chemical processes to occur which couldn't occur without us. One example that we've been doing for a long time, steel making. Iron and steel making is a chemical process. We use heat to make a physical change in the metal. We throw in other components, different chemical components to bond to different parts of the ore to separate out the metal from different parts, right? There's a whole multi-stage chemical process involved in making iron or steel, right? Medicines today, primarily, even though we should be far beyond this, medicines today is largely based on chemistry, our ability to synthesize new kinds of chemical compounds, which wouldn't have existed otherwise. A lot of the chemical compounds we produce today are created within artificial environments, right? Higher heats than would have existed otherwise. We bring these things about. That comes from our understanding of chemistry. Now, around the 1880s, 1890s, you have the emerging science of the nucleus. The phenomenon of radiation began to be observed, cataloged, and understood. The idea that there was actually something smaller than the atom, that the atom was actually a composite, first came to light. Now also around the turn of the 20th century, you had the work of Einstein that proposed the convertibility between mass and energy with his famous E equals mc squared, with the idea that a small amount of mass can be converted to a large amount of energy. So it was in this environment that fusion conceptually was born. Both fission and fusion. So when we're talking about a nuclear economy, a fission or fusion economy, we're talking about something which is much beyond chemistry. Whereas in chemistry, our powers are based on causing new chemical combinations of different kinds of elements. With nuclear processes and our ability to change the nucleus of an atom, we're actually changing the elements themselves. So no longer just combining elements to make something new, we're actually taking a chemical element, carbon, gold, whatever it is, and we're able to actually change and sculpt that element itself to have new properties. So I'll talk a little more specifically about that, but if hopefully people can get a sense that it's a whole other level of our power over matter, a finer and more powerful degree of control over matter. Now what you see up here on the screen is what you see up here on the screen is a schematic of a fission reaction. Now people are familiar, we have nuclear fission plants today. The basic form of a nuclear fission reaction is you have a large heavy element, typically uranium, which has a very heavy nucleus. And that nucleus is split apart when we hit it with something like, we can cause a neutron to strike the heavy nucleus, causing it to split. Now here's the interesting thing, is that the mass of this heavy nucleus, and so you see when it splits, you have two, or sometimes many more, new products, new elements are created. You also have other particles which come out of this thing, neutrons in this case. Now the interesting thing is that the uranium or whatever nucleus you start from, the mass of that is not equivalent to the mass of all the products. Okay? The mass that you started with is actually heavier than the total mass of all of the products that come out of it. Why? Because some of the mass was converted into energy, which we see in the heat of the reaction, the heat released of the reaction. So man figured out how to actually cause fission to occur such that we could harness its power. Now, fusion is beyond that. Fusion is, at a surface level, fusion is the inverse process. Rather than splitting apart an atom, the idea of fusion is bringing together two different atoms and causing them to unite into a new element. So the fusion, most of the fusion work that's being done today is fusing two types of hydrogen, which is the lightest element. We have deuterium, because it has two parts to it, and tritium, 3. So these are two kinds of hydrogen. So with fusion, we have the uniting of these two to create a new element, helium. And then we have the release, so we have the helium product, the release of a neutron, and a lot of energy. So that's the concept, is that you're actually changing the atoms and the elements themselves and creating something that didn't exist before. Now, the interesting thing is that while on the surface you'd say, okay, fission and fusion are just the opposites of each other. Fission is breaking things up, fusion is putting things together. They're actually not just inverses of each other. They're actually not really equivalent at all. They're, as we're coming to find as scientists are coming to find in doing the work on fusion, they're very different. And we see that partially in difficulty. Fission was achieved first in the 1940s? And here we are in the 21st century. It's taken a long time. But the other more important way that they differ is in their energy density. And here's where we get back to the issue of energy flux density that I brought up a few minutes ago. So what this table compares, you see in the left-hand column there, you have different fuel sources: wood, coal, petroleum, natural gases. Then you have nuclear, right? These two columns are nuclear with uranium fuel. And then you have fusion. And then beyond that, we have something we theorize exists but haven't done yet, which is matter-antimatter reaction. So those are your fuel sources. Now if you look on the left here, what we should do is just look at this order of magnitude, 10 to the whatever on the right here. You see with wood, coal, petroleum, and natural gases, we're dealing with a certain order of magnitude in the tens of thousands. Then as soon as we get to nuclear, we're dealing with something in the billions. Billions, tens of billions. And then as soon as we get to fusion, we're dealing with something in order of magnitude even more dense. And what that means is that per unit of fuel, per gram of fuel, you have an order of magnitude more energy in fusion reactions than even fission reactions. So that's one glimpse into what we're dealing with, what would be implied by humanity now going not just to a fission economy, but to a fusion economy. But the other thing that's important here is that with fusion, this would also be true with fission compared to what we have now, but when you talk about shifting from a petroleum or even fission economy to a fusion economy, we're not just talking about a fusion electricity economy. We're not merely talking about the fact that now we produce our electricity mostly in coal and natural gas plants, some fission plants, but in the future we'll produce electricity using something different, and then we'll discover something better, and we'll produce electricity using something different, right? It's not just that, it's that fusion, as I said before, gives you entirely new capabilities. And so you're talking about a total qualitative transformation of every part of the economy when you go to basing your action on a newly discovered principle. So I wanted to give two or three examples of things that actually already, in this case, already exists, although it's part of the work that has been done over the past decades on fusion, on discovering fusion. So this is a picture of a laser. This is a very special laser housed down at the University of Texas in Austin. And this laser is a petawatt laser. So I don't know, anybody know what a petawatt is? It's 10 to the 15th watts, or a quadrillion watts.
Wow.
So this laser can deliver a quadrillion watts of energy. Now to give you some, because that sort of blows your mind and it's hard to even think about what that means. Just for a very simple comparison, a quadrillion watts is roughly, if you delivered a quadrillion watts of energy over 1 second, that amount of power is equivalent to leaving your 60-watt light bulb on for 13 billion years.
Wow.
So that's the kinds, now they don't leave this on for a full second. And here's the very special thing about this laser is that it delivers that amount of power. The reason it's so powerful is because it delivers so much energy over 150 femtoseconds, which is 10 to the negative 15th seconds. Or a femtosecond is a quadrillionth of a second. Mm-hmm.
Is that power to like a thing, like in space where there's no atmosphere, or is that something that could be utilized only in an atmosphere?
No, it can travel through space.
Yeah.
Yeah.
So that would be great for, let's say, asteroids.
Exactly. Yeah. So here's what.
Protecting us from the.
So this thing is incredible, and we already know that we're going to be able to do certain things with it. One thing is that lasers like this can be used very efficiently in surgery. Mm-hmm. And here's the interesting thing is that because this laser acts so quickly, it can, if used in surgery, it can be used to target and vaporize a cell without the next neighboring cell noticing that anything happened.
Wow.
So there's no heat transfer, there's no damage transferred to surrounding tissue. You can target a cell and vaporize it without having any effect on the surrounding tissue at all.
Do a lot of diseases.
Yeah.
All that stuff.
Yeah, and the other thing it can do similarly is we look up here, this is actually, this might be interesting to some of you. This is applications to dentistry. But what you see here on both of these are pictures, up close pictures of teeth.
A what?
A tooth. A tooth.
Okay.
And the picture on the left is the effect of zapping the tooth with a typical surgical laser, right? Which is, this shouldn't make you pessimistic about regular lasers. They're also much better than anything else we have, including your dentist drill or anything else. But just for comparison, this is the effect of a regular laser on a tooth, and you see all the slag, you see the crack and the surrounding damage. This is the petawatt laser.
The what?
This is the petawatt, the green laser I just showed you. So this is a regular laser, the kinds that we would have, the kinds that we wield today. And this is the petawatt laser for comparison. Now this down here, this is a picture of a cut through stainless steel. This is a regular laser, and you see the jagged cut, and you see all the
Is that
slag.
like a torch, cutting torch type of thing?
It's a laser. It's a cutting laser.
That's
Exactly.
the torch C is.
Yeah, and this is a cut from a petawatt laser.
Wow.
Clean.
Yeah,
It's a cleaner cut.
it's amazing. It's totally. I mean, if you compare the laser to
Yeah.
to a metal
It's
like a metal cutting machine, I don't.
Like a plasma.
This is incredible compared to your metal on metal cutting. But then you compare that to the petawatt laser, and I mean, I was just thinking, back in the space program during the Apollo program when industrialists and manufacturers were challenged to create parts that had to be within, microns or nanometers of precision. And then you see that, and that was right. And then you see what could think about what could potentially be done with these kinds of lasers.
Is there any way you could describe how does that focus in on a certain cell and be able to be so accurate?
No, I've not looked so closely into it. Yes.
Huh?
I saw on TV on the news
I
that
can't hear.
people were shooting laser beams at
Oh.
planes, at airplanes,
Yeah, I don't know.
blinding
I don't know.
them
Did you have a question,
sometimes.
Marcel?
It's not as powerful as this laser, but they were shooting laser beams, committing crimes that blinded a few pilots. So it was amazing.
Just if you know, what is the general magnification of these images you're showing?
I don't know, actually. I don't know. But what I will tell people is that my colleague, Liana Fan Chang, will have an article out by the end of the weekend, which has this picture in it, and she will have a caption.
Is that gonna be on the website?
Yeah. Yes, it will be on the website.
It's not here, you don't have it.
No,
set
it's
up.
not quite ready. She's doing the final edits of it. Now the other, and then the other thing that the petawatt laser is useful for is that it can be used to directly accelerate particles to transmute other elements. So I don't know if people know this. We currently use big machines called particle accelerators, which will have to send a particle over, basically the equivalent of miles and miles of distance in order to accelerate it to very, very, very high speeds. And we can use these particles to do things like create isotopes, like smash it into another element and change its composition. The petawatt laser can, in a very short distance, can accelerate particles so that we can slam them into things like gold and create a new element out of it. They used gold to create platinum, I think. So this is another potential that we have. So you're literally compressing space and time. Now the other aspect of the fusion economy I wanted to discuss is something that we do not currently have, but we know that we could have. And that is something that was invented in the 1960s called the fusion torch. And this is a potential application of a fusion reactor. So the idea is that within a fusion reactor, and we'll look at some pictures of some fusion reactors in a minute here, but within a fusion reactor you have something called a plasma, which is a state of matter beyond a gas. It's a gas, but it's an ionized gas. It's charged. It's at super high temperatures, and it behaves much differently than a gas. And the idea of the fusion torch is that from this fusion reactor, you can divert some of the plasma off to a special section called the fusion torch, where as that plasma is guided through this section by magnets, you can drop in solid feedstock. So for example, scrap metal, or trash, or ore, low-grade ore that was mined out of the ground. Anything that we know of could be dropped into the fusion torch, and because of the high temperatures of the plasma in tens and potentially hundreds of millions of degrees, that material is not only vaporized, but it's completely dissociated. So all of the constituent elements of that material are separated and broken up. All the electrons are stripped off, and they become part of the plasma. Now what that means is that this new plasma, which is made up of all this stuff that you dropped into it, can then be passed into a separation chamber. And there are many different methods of how you could separate those different elements and start to literally manufacture a new metal deposit or a new, X, whatever, deposit of this material. And that's due to the unique state of matter of a plasma and the fact that we can potentially create these things hot enough in high enough volume to literally use this as a new universal mining machine in a certain sense. So this is, again, these don't exist yet, but will exist in a fusion economy. So that's just to give people a little bit of a taste of what we mean by a new capability. Because it's not that you will never burn enough coal to do this, ever. Even if you had trillions of tons of coal, no amount of coal in the world could produce the kind of concentration of heat to do this.
This looks like a new type of fancy recycling machine.
That's actually one application of it, yeah. Yeah, that was one of the creators of it were thinking of that. How could you actually deal with,
If it separates itself that way, as you said.
And the interesting thing, because you think about recycling, when you recycle, you're doing that with things that we already use. So when you take trash from landfills, that already contains, everything contained in there is stuff that we already use in our manufacturing process. It's products that were consumed and then thrown away. So you can actually reprocess that. Right? You don't have to go out and get more metal from the ground. You can just reuse it right there. And so hopefully you got in a sense of the kinds of.
Excuse me.
Yes.
You're saying we can put trash in there. What about that new mineral that the Chinese are going to the moon to get?
We'll talk about that in a minute. That would also be, you could also dump that in there. If it were part of something, it would be affected the same way.
Would it be more efficient than putting trash in there?
Mm-mm. No, the trash isn't the fuel. The trash is actually what is being processed. So the fuel comes from the fusion reactor. And then part of the plasma, part of the gas of that fusion reactor could be pumped through and used to treat and process trash or some materials. So that's actually the product.
Okay, so if you can't use that new element that the Chinese are getting, what's it called?
Helium-3.
Helium-3.
Yeah, that could.
be one more.
Well, we're gonna have to do.
Power plant to use helium-3.
Yeah, we're gonna have to use the helium-3 for is in the fusion power plant itself, in the fusion reactor itself, to actually fuel.
To run it.
To run it. Yeah, exactly. Now I just wanted to.
Is that self-generated?
What do you mean?
Replicate itself, so you don't have to keep getting more?
You'd have to keep getting more and feeding it in there.
But it's deposited by the sun, so it keeps on coming on the moon.
Yeah.
You just have to.
Well,
Good
yeah, there's.
source.
There's about a couple billion years of helium-3.
Oh.
Yeah.
I'm like, I don't know.
It's pretty abundant. Yeah.
But now, right?
Yeah, exactly.
Here, 40,000. We're running out of fuel.
Yeah, right. So, my colleague Leona in her article, I thought, put it very well when she was, in the beginning, she discusses fusion. And she says, what she points out is that fusion was first used by man in an uncontrolled way in the fusion bomb. But simultaneously with the creation of the fusion bomb, you had the idea that we have to learn to control this for the good, for development. And so she says that the challenge very quickly became to perform the more difficult task of controlling fusion. So more difficult than the bomb is to actually control fusion as a power source, and to unlock the myriad potentials in that capability. So she says, the pursuit of controlled fusion, all the work that's been done since the 1940s, has led to the creation of temperatures 100 times that of the sun. So the temperatures that we can already create in fusion research are 100 times that of anything we know of on the sun. It's led to, and also she says hotter than any star that we know of out there. It's led to the creation of power densities which can vaporize a cell, which I already told you guys about. And she said it's led to the creation of densities of material which are 100 times the density of lead and 10 times the density of the center of the sun. So even in just fusion research, the incredible research that's gone on, we can produce temperatures many times hotter than the sun, light many times brighter than any star that we know of, and densities many times greater than the core of the sun. So when LaRouche, if you hear LaRouche talk about man subsuming the solar system, this is kind of what we're talking about, is that man is in potential in his capability now, in the potential of his capability, man is more powerful than the sun itself. So what I want to get to now is a little bit of history of fusion in the United States and why it is that we don't have fusion today. So a big part of the history of fusion in the United States is Lyndon LaRouche and the Fusion Energy Foundation that he helped found in 1974 in collaboration with some of the greatest nuclear scientists in the world, one of which was Dr. Robert Moon, who had worked on the Manhattan Project. And so the Fusion Energy Foundation was founded in '74. It was based in New York City, and the FEF played a completely unique role in, not just in fusion research in the United States, but it played a completely unique and crucial role in the United States itself. Over the period from '74 to '86, we sponsored dozens upon dozens of seminars internationally of fusion scientists and others to come together to collaborate and discuss the crucial questions of fusion and the economics connected to it. We had, we led many of the political fights that publicly a lot of these scientists who worked for national labs or other such organizations couldn't publicly fight. People who might have met us back in the day, I don't know if there's anybody in the room, might have met us in an airport. The Fusion Energy Foundation was famous for not only being in airports and meeting people, but being out in society, right? And here's the profound thing. We were out on the street corner with book tables, briefing and educating the American population about fusion, about what fusion was, about what the fusion economy was going to bring, about why they should fight for it. So this was crucial for the advancements of fusion that occurred in the United States. And we were in touch with all of the top people who were running the national labs. We were feeding LaRouche's ideas directly to these people, his proposals about different fuel potentials, different things like this. So as I go through this, I want you to remember that I mean, really, LaRouche is really crucial, has been crucial to the history of fusion, and clearly will be crucial to the future of fusion. Now, the U.S. fusion program actually began very early. It began in the 1930s. In 1936, there was an attempt, there was a very low-budget attempt, sort of, quiet project that was kept very quiet, an attempt to achieve fusion at the Langley Aeronautics Lab, which is now the Langley National something lab. It's part of NASA now, down in Langley, Virginia. There was an attempt to create fusion, didn't work, but the young scientists' work actually inspired continuing work on their concept into the 1940s. Throughout the 1940s, we're obviously at our national labs like Los Alamos, Livermore, we had work on bombs, on fission and fusion bombs. But interestingly, those same scientists that were working on bombs were totally convinced that this was going to be a great, once we actually defeated fascism, these capabilities were going to be the great power for peace. And so literally the same people in the same programs were doing work, small scale work on nuclear fusion. Now this really became serious in the 1950s In 1951, the United States launched a classified crash program for fusion called Project Sherwood. And the reason it's named Project Sherwood is sort of a funny fact. It's because one of the main personalities and fusion scientists in fusion in the United States at Los Alamos was named James Tuck, and they called him Friar Tuck. So they called the project Project Sherwood. And Project Sherwood was, like I said, a very focused crash program. And there was a steering committee. There was a 3-man steering committee, or maybe 4-man, of Project Sherwood, including Dr. Edward Teller, who Lyndon LaRouche worked closely with and worked with the Fusion Energy Foundation. And they would meet periodically to review all of the work that was going on at the labs, decide what had the most potential, decide what to encourage. So they had an overview of and they were steering the entire thing. They had bi-yearly seminars in different places around the country where these scientists at the different labs could actually come together for a week, or maybe it was half a week, and actually have an intense dialogue and collaboration and brainstorming session around these ideas, review everybody's work. And during Project Sherwood, there were 3 main designs for fusion reactors that were being pursued in the United States. And I don't want anybody to get confused by the technical details. What I want you to get out of this is that there are very different approaches that you can take to fusion. So the first one is called the pinch, which is interesting. And the pinch happens because you run an electric current through the plasma. And when you do that, the plasma, which is traveling in this direction, starts to attract, the different plasma particles start to attract each other. And so all the plasma fuel begins to pinch down into the center of the tube and eventually collapses into a very dense line, a very dense filament within the middle of the tube. And the idea is we can use this to force fusion. So that was one design. Another design is to have the fusion gas going around within this donut, this torus, and use a magnetic field to twist it because they thought that would make it more stable and to create fusion there. Another concept was called the mirror, where you have a straight tube and you have 2 very powerful magnets on the end of it. So it's a tube with an open cylinder, powerful magnets on the end, and the idea is that the fuel, as it heats up in the center, it starts to go out toward the magnets, gets reflected back, and then comes back and fuses. So these are all really interesting approaches. Now the 4th one is called the tokamak. This actually, the United States did eventually work on tokamaks, but it began in Russia. And it's a similar design to the stellarator, although it doesn't twist, and you use magnets both around the tube this way and around this way to confine the fuel.
They're doing that in Princeton?
They're doing, yes, they want to do this in Princeton, and they are doing this in Princeton. And so so the initial work, the really, I think, very exciting work a lot of it did happen right around here in Princeton. I'll get to what this is in a second. I did want to, or no, I might as well just show you. I just had some pictures of the early machines, which I think are really interesting. This one it's the pinch design, although it's round. And it was named the Perhapsatron by James Tuck. And the reason he named it is because he said, perhaps it'll work, perhaps it won't. But I want to try it. This is a more advanced it didn't work. This is a more advanced version of the Perhapsatron at Los Alamos. I think that was 1956. This is a stellarator at Princeton. And the interesting thing about the Princeton program is that Lyman Spitzer, who was the first head of the lab and who invented the idea of a stellarator to begin with, he had a design concept for stellarator A, B, C, and D. And this is in 1952. And he thought stellarator A is going to be the first attempt, B is going to be an improvement, C is going to be a physics test proving that we can actually make fusion in a sustained way, and D is going to be a demonstration reactor that's going to put electricity on the power grid. So he had this vision from the beginning, and by the time when his program was finally shut down, they were on, or changed, they were on C model, or moving toward the C model. This is an early mirror machine. So you can see the tube here. You have these big magnetic structures, and then then you would have these big magnets on the end. And this is the very first tokamak in the Soviet Union. Now the thing that happened, this is the tokamak 1, tokamak 3 actually I shouldn't get ahead of myself. I'll get back to that in a minute. I did want to read a couple of quotes from the head of the Atomic Energy Commission during Project Sherwood. His name is Louis Strauss. I just thought he expressed very well what the point of the fusion program was. So, and now as I read this view was shared by almost everybody working on the project and leaders internationally. So in 1954, Louis Strauss said about fusion, he said, "Our children will enjoy in their homes electrical energy too cheap to meter. It is not too much to expect that our children will know of great periodic regional famines in the world only as a matter of history. They will travel effortlessly over the seas and under them, and through the air with minimum of danger and at great speeds. And they'll experience a lifespan far longer than ours, as disease yields, and man comes to understand what causes him to age." He said in 1958, "The importance of Project Sherwood as the importance of Sherwood, as the project was called, now conceded to be at least theoretically possible, can hardly be overstated. And I hope to live long enough to see the same natural force which powers the hydrogen bomb tamed for peaceful purposes. A breakthrough could come tomorrow, as well as a decade hence. Out of our laboratories may come a discovery as important as the Promethean taming of fire." And so Louis Strauss was the head of the Atomic Energy Commission and the project throughout the 1950s. In 1956, they began the declassification of the project. In 1958, the project was fully declassified as part of an international conference on atomic energy for the purposes of collaboration. So the idea was declassify, you have work going on in the United States, you have work going on in the Soviet Union, a little bit in the United Kingdom, and the point is collaboration. So in 1958, the project is declassified and international collaboration begins. Now at that conference, the president of the conference, who was the head of the Atomic Energy Commission in India, Homi Bhabha, he said about fusion, he said, "I venture to predict that a method will be found for liberating fusion energy in a controlled manner within the next 2 decades. This was the 1950s, within the next 2 decades. When that happens, the energy problems of the world will have been solved forever. For the fuel will be as plentiful as the heavy hydrogen in the oceans." So he pointed to something important. Where does the fuel for fusion come from? The deuterium that I showed you, it's in the ocean, right? Completely overturns the British game of bottlenecking resources, controlling strategic raw materials, right? The fuel can be found in the oceans. So that was the optimism of fusion.
Wasn't something like this done and then shut down, just like as you said, they couldn't measure it and meter it and charge you for it?
Yeah, well it wasn't just about the money though, it was about the fact that if nations had access to this kind of power, then their development would be unlimited, right? Then sovereign nations would have the power to develop unlimitedly, right?
Yeah.
The empire is over. So yeah, it's not just about the money or some kind of corporate interest, it is this larger question of the development of man.
Of the game.
Yeah.
They want to control everything.
Yeah, so, okay, so it's declassified. Something I'll mention, although not get into, is that another important approach to fusion began in 1960, and that is called inertial fusion, which is, people have seen what's happening at the National Ignition Facility with all these lasers that are impinging on this tiny little target to try to compress it to get fusion. Right, that actually began in 1960, which is the same year that the laser was invented. So that was important. Now, throughout the 1960s, all of these different types of fusion devices made tremendous progress. And the United States was committed to supporting fusion research. In 1951, the fusion budget was $70 million. Now these figures I'm giving you, that's current dollars, that's not $1950, but the fusion budget was $70 million in 1951. By the end of Project Sherwood, it was $114 million. So there was a total commitment to this thing. By 1968, the budget was $140 million. So with that kind of backup to the fusion research that was going on, we really had a lot of potential. In the beginning of the 1970s, you had a lot of expansion within the national labs of different kinds of fusion research that were going on. You had the expansion of fusion into industries, like General Atomics, for example, was brought in the 1970s into fusion research. Their scientists were given security clearances and whatever they would need to have access to fusion research. And then today, people may know that General Atomics has one of the most important fusion research machines in the world, their D3D tokamak. You also had the expansion into universities. So we were beginning to think about educating a new generation of fusion scientists already in the late 60s and early 70s. Now, also in the early 70s, because of this optimistic perspective of what had been accomplished over just the past decade and a half, 2 decades, there were 2 important studies done in the beginning of the 1970s. This one was a study which was done, it was a complete mapping out of different possible timescales for when we could achieve fusion. So this is 1974. The study was done which basically mapped out every step in 5 different possible pathways to achieve fusion. The earliest would have put a demonstration fusion reactor on the power grid by 1993. So what these curves represent are the amount of funding per year that would have to go into the program based on different stages of investment. So you see 1993, there was a second one proposed, 1998, there was another one proposed, wait a minute, oh sorry, this blue one is 1990, was the earliest proposed date. 93, 98, the most conservative proposal would have put a demonstration reactor on the power grid by 2005. And then to really underscore the point, there was also a funding curve called Fusion Never. What is the level of funding at which we will never get fusion? So that was known, right? Not that that was a proposed idea, but that was known, like to warn people, hey, if you don't make the necessary investments into these different components of the research, you're never gonna do it. Now this dark black line, that's the actual funding of fusion.
That's amazing.
Yeah. Yeah, so, but here's the point to make, is that this was the early 1970s. We knew what it was gonna take. We had been through 20 years of fusion work so far. We had competent people at the head of the Atomic Energy Commission who were committed to it, and they knew what it was gonna take in terms of levels of investment to get there. And what's the actual funding been over the years? It's a total fraud from that standpoint, right? If somebody says, oh, well, the scientists just haven't figured it out yet, right? This is the truth. Now, the other thing that was done in 1972 was a study mapping out what are the necessary milestones that we can expect in this process. And that 1972 study pointed to 2 very specific milestones. One had to do with this machine, the Princeton Large Torus, which was at that point the most advanced tokamak fusion machine that we had in the United States. So in 72, they said that they expected very significant results from the Princeton Large Torus, or the PLT, in terms of the temperatures that the PLT was going to be able to achieve. And they expected those by 1978. The second thing that they expected, which was going to be very significant, was that there's a follow-on machine to the PLT called the Tokamak Fusion Test Reactor that Princeton had planned, the TFTR. And they expected the TFTR to build upon what this machine had done, and that the TFTR would be able to produce 10 megawatts of fusion power, which was at that time, well, it still is, enormous, right? It's still pretty big. And that the accomplishments of TFTR would lead directly to a demonstration reactor. So that was the idea of the milestones. Now, so this is the Princeton Large Torus. I'm going to say something much more about that in just a moment. There also simultaneously, or a couple of years later, you have the building of a machine out in California at Livermore. This is, remember that mirror machine I showed you, that little tiny tube inside that magnet? This is its great-grandson or whatever. This is the several phases down the line version of the mirror machine. And this was, I'll say something about this in a few minutes, but this was being constructed at Livermore, and you can see the size of the people for scale here of what we're talking about. So this was achieving the same kinds of successes that were being achieved in tokamaks in terms of temperatures, the time that we were able to get the fuel to stay in one place so that it could react. We were making great strides with this machine. Now, back to the Princeton Large Torus. Now, the PLT took up a very significant place in fusion history, and it involved LaRouche's Fusion Energy Foundation. In July of 1978, the PLT achieved a temperature of over 60 million degrees inside this thing. Just to give you a sense of it, the hottest temperature we know of on the sun is 27 million degrees. This is more than twice that inside this machine. That's the first time that had ever been done. 60 million degrees was the temperature threshold for a sustained, in terms of theory, what we think is the temperature threshold to be surpassed if we're going to get sustained fusion.
And
So
this was how much?
this is just over 60 million degrees. So that's July of 1978. Now there's a fight that immediately takes place. Immediately the leadership of the Department of Energy, James Schlesinger, I have such a hard time with that name, Schlesinger, puts the kibosh on it. Tells the head of the lab, Mel Gottlieb, you can't release your results yet. We have to review them. Now, news gets out that this had happened. Come early August, news has gotten out to the media. There's a ton of buzz. The Fusion Energy Foundation gets involved because there is an obvious clampdown from the top to not let this news out. Now, the official lines that finally are forced to come out from the Department of Energy spokesman, George Keyworth, is that, yeah, something happened at Princeton, but it's not really that important, and fusion is just as far away as we said it was. And that's almost verbatim what the official statement from the Department of Energy was. Now, the head of the Fusion Energy Foundation called the White House and informed the White House that there was supposed to be a press conference, which had been temporarily canceled by the Department of Energy. Notified the media. Now, somebody that we were in contact with at the time, who was in the Atomic Energy Commission, named Stephen Dean, he was quoted in the media in terms of being leaked to the media. He said of this development, he said, the question of whether fusion is feasible from a scientific point of view has now been answered. It is the first time that we've produced the actual conditions of a fusion reactor in a scale model. Now, this breakthrough, and Dean described it well, right? Now the question of whether fusion is feasible has been answered. This should have set off a total mobilization, because I forget the exact time frame, not too long before this, you had already had some of the key parameters to achieve fusion achieved in another machine at MIT called the Alcator. The Alcator had achieved a confinement time and a density of the fuel that met the requirements of fusion. Now we achieve the temperature that you needed for fusion. So a sane society would, the president would have immediately called a crash program mobilization. We're gonna make the design, we're gonna get this all in one machine, and we're gonna do it. That's not what happened.
What's the date?
July 1978.
78, who was the president?
Carter.
Oh.
Now, why would they say that this is not a breakthrough? You don't need to hear about it, right? Now, just to tell you, the press conference did go ahead, and we made sure the world knew. But why would the kibosh have been put on this? Well, let me give you a sense of why somebody like Schlesinger would have been installed at the DOE. Here's something that he wrote in 1960 in a book called The Political Economy of National Security. He said, "Economics is the science of choice in a world of limited resources. We have gone around spreading the gospel of plenty, raising the level of expectations. But in the nature of things, these rising expectations can never be satisfied. We must, in our strategic policy, return to the days before the Industrial Revolution and prepare to fight limited warfare." So that's his perspective, right? This is the disgusting Malthusian perspective that was intentionally installed by the empire in US leadership after they killed Kennedy. And you contrast this statement with what was said by John F. Kennedy, right? The kind of optimism of Kennedy. Now, not everybody was like Schlesinger. There was a very important congressman that our organization worked very closely with. He was from Washington State, named Mike McCormick. Oh, there he is. And Mike McCormick, this is him speaking at a Fusion Energy Foundation conference in 1980. And Mike McCormick immediately seized upon the breakthrough at Princeton to convene a special committee, or a special committee, a study committee in the Congress to study the prospects for fusion energy coming off of this breakthrough. And in 1980, in January, he introduced into the Congress legislation called the Magnetic Fusion Energy Engineering Act of 1980. And the act the purpose of the act was that we were going to get fusion by the year 2000. And so it outlined a funding regime and a series of steps to be taken by the United States to get fusion. Number one, we were going to immediately build a new facility for fusion engineering. And what we mean by engineering is that we are able to take the scientific breakthroughs and figure out all the challenges with the materials and the magnets and actually build the thing. So by 1987, we were to have a new enormous fusion engineering facility to do this. And we were going to have a demonstration reactor putting power on the grid by the year 2000. Now he introduced this. This was voted up overwhelmingly by the Congress in October of 1987. I had the vote. The exact vote here was like 300 and something to 7. Right? It was enormous. Sort of. Yeah.
1980.
It was 1980, and it was signed by Carter in October of 1980 into law. This was the law of the land of the United States, October 7th, 1980. Now what happened is congressmen like McCormick and many other good people were voted out of office a month later, not because the population didn't appreciate them, but because Jimmy Carter conceded early in the election and many Democrats on the West Coast didn't vote. And so Democrats like McCormick lost their election. Now, I just want to go a little bit into what followed on that, because this was really, that really was the moment of great potential that should have been seized. Instead, you had the continuation of this Malthusian Wall Street policy take over.
But you said it was written in like law, but who changed it?
Well, here's what happened, is that it is still law. It's still on the books. It was voted in by Congress. It was signed by the president. But here's what happened. It was never funded. So as soon as Reagan's administration comes in, it was 365 to 7. As soon as the Reagan administration comes in, they introduce a fusion budget, which level is not only not up to what is mandated by the law, it's lower than the 1977 budget. And the science advisor to President Reagan, his name is Doug Pewitt, he, oh no, I'm sorry, this is still George Keyworth, he's still in there. He said, this was his reasoning. So the first thing that Keyworth announces is that the budget's cut, the 1987 fusion engineering facility that we were supposed to build, plans were supposed to be introduced by the Department of Energy in 1981. Keyworth said, we really shouldn't build this thing. It's premature. We should just use one of our existing facilities and start to do research on fusion engineering. So they canceled it. So what's that say, right? What that says is, you can do all the research you want, we're never gonna build it. We're never actually going to allow the thing to be built. Now he said, when he was testifying to Congress, Keyworth said, the United States cannot expect to be preeminent in all scientific fields, nor is it desirable. He said, it is not the government's responsibility to conduct energy R&D and pursue energy independence. It's the responsibility of private industry. Now, no private industry can put up the money for this. So then he said, he said, actually, abundant funding can promote mediocrity rather than stimulate excellence. So again, compare that to Kennedy. Now, I just want to get through quickly because I know I've gone through a lot so far. Despite the budget cuts, this was the follow-on machine to the PLT that I mentioned. This is the TFTR, which was built and finished in 1986 and immediately began making breakthroughs, even though the environment was already closing in on fusion research. The TFTR, and I'm a real fan, it started operation in 1982. It produced a record temperature in 1986 of 200 million degrees. Wow. 200 million degrees. As soon as that milestone was reached, scientists at Princeton began designing the follow-on to this one, which was going to be the precursor to a demo reactor. Now that was never built. And actually the Chinese took our plant. We gave our plans to the Chinese because they wanted them and they took it in their building. So the TFTR in 1986, 200 million degrees. In 1994, now this is 10 years after it was forecast, but in 1994 this machine produced 10 megawatts of fusion power, which was this great milestone. In 1995, it produced a temperature of 510 million degrees. Okay. In 1997, anybody remember who was Speaker of the House? Gingrich. In 1997, the TFTR was shut down and mothballed. And they began to take it apart. And it was taken apart and finished in 2002. Now there was no scientific reason for that. No scientific reason. It was all budget. And the idiotic head of the Energy Committee said we shouldn't waste any more money on this stuff.
Where was this?
This is Princeton.
Oh, that's at Princeton too.
Yeah, this is at Princeton. During this time, there were something like 800 employees at the PPPO, which is awesome. I don't know what they're down to today. It's much, much lower. And then I can say as soon as the follow-on to this one was canceled, even it was never built, but they had plans. As soon as the follow-on to this one was canceled, they had to start laying people off. And so all this knowledge was scattered. It's not just that somebody has to find a new job, it's that you had teams that were assembled that actually had a certain collaborative process of thinking and problem solving, and they were then scattered. So since then, you've had a complete downslide of the U.S. fusion program, and this is not the fault of the scientists. This is the fault of an intentional policy to shut it down. Now, since that time, the United States has been participating in a project called ITER, which people might have heard of, the International Thermonuclear Experimental Reactor, which is being built in France. The first agreements for ITER were signed in 1985. So the ITER tokamak, which is very exciting, it's very large, it's going to produce 500 megawatts of power, it's going to sustain it for I forget how long. That was designed basically in 1985. So it's very good that it's being built, but we should have been way beyond that by now. So the main activity the US is engaged in, and almost all our fusion money is going to our obligation for this international project. Now there's also good research being done, like I showed the petawatt laser in the beginning. That was supposed to be part of a fusion program. The fusion part got cut, we still developed the laser, which is very good. But the point is that the national mission has been lost. The kind of mission orientation that we had from 1950 up until 1978 or so, the mid-70s, is lost. And that's because of the empire policy. It's because of what I read in the beginning from Henry Carey. It's because the American system has been subverted to the English, the British system. Now, that brings us back to today and the mission of what this newly forming economic system has to take up. And as Diane mentioned in the beginning, the leadership in that and the most forefront example, the people who are actually setting the standard for the world in this and in the economic system is China. China has a robust, incredible fusion program. So I just want to say a couple things about that and then we can open up for discussion. So China is doing two very important things which they see as the same thing. They are pursuing fusion and they're going to the moon. Now, what makes it very clear that they see it as the same thing, and that's not just my spin on it, is that they assigned a single person to be the director of the space program and the atomic energy program and also the defense program. Not the Minister of Defense, but he's in charge of the technology of the defense program. So a single director to coordinate all these fields. Now, in terms of fusion, China has a tokamak called the East tokamak, which is basically a sister tokamak to this one. Except with one very important exception, they're using something called superconducting magnets, which are just way beyond the magnetic potential of what this tokamak had. So they have something called the East tokamak. They are already making concrete plans to build a demonstration tokamak. So they will begin construction of this demonstration tokamak within the next decade. They also have just declared that by the end of this decade, they will graduate 2,000 PhDs in fusion science. So you imagine that, 2,000 young people in the course of a decade graduating as fusion scientists. Now to contrast that quickly, in the United States, we have a very important fusion machine at MIT called the Alcator that I mentioned. Alcator would have been shut down a couple of years ago. They just restored the funding to Alcator, but the only reason they allowed the funding to be restored is so that the current students could graduate, and then they're going to shut it down. So you see the contrast there.
Excuse me, what is that Alcator again?
It's a fusion research machine at MIT.
Oh, it's a research fusion machine. The guy that you had in the picture that was giving the speech before,
Yeah.
he looked like Henry Kissinger, but what was his name?
Mike McCormick. McCormick, yeah. Yeah, he's very different than Kissinger.
Looks almost like that.
It's the glasses. Anyway, okay, so that's just a quick sense of their fusion program. In terms of the moon, China is going to go to the moon, and they have an extremely ambitious program. I just want to read a couple of quick quotes from the head of the space program. And I'm going to butcher his name, so for anybody who speaks Chinese, I'm very sorry. So this is Ouyang Zhuan, I think, who is the father of the Chinese space program. And the Chinese, in 2004, the Chinese announced their lunar program. Now, this man, who's the head of the program, he said in a recent interview, he said, the moon has huge reserves of metals such as iron. It also has helium-3, an isotope of the element helium, which is ideal for nuclear fusion power, the next generation of nuclear power. It is estimated that reserves of helium-3 across the Earth amount to just 15 tons, while 100 tons of helium-3 will be needed each year. The moon, on the other hand, has reserves estimated at between 1 and 5 million tons. The moon is full of resources, mainly rare earth elements, titanium and uranium, which the Earth is very short of. And these resources can be used without limitation. There are so many potential developments, it's beautiful. So we hope we can fully utilize the moon to support sustainable development for humans and society. And then he just went on to discuss how they're assembling their own a team of intellects to conquer these challenges. Now, in terms of what the Chinese have announced about their lunar program, we already saw last year the Chang'e 3 launch, where the Chinese made the first soft landing on the moon since the 1970s. The United States was the last country to make a soft landing on the moon, as opposed to a crash landing, right? So the Chinese, the Chang'e 3, made a soft landing on the moon, and it has a rover vehicle which drove off and started roving around the moon and communicating with the scientists on Earth, which is incredible. China is the only other nation to do that. Now, the rover has since stopped operating because of technical complications, but the Chinese said this was a great success, and the mission accomplished what it was designed to accomplish, and we've now learned what we need to learn for the next step. So what they have planned is the next launch, Chang'e 4, is going to launch a rover very similar to the one on the moon, but with equipment for sample return. It's not going to have a sample return, but it's going to test out the equipment. Chang'e 5, which was going to launch in 2017, just 3 years from now, is going to launch as a sample return mission to go pick up whatever they're going to pick up, lunar soil, whatever else, and bring it back to Earth, return to Earth. Now, they also have done tests on a self-sufficient lunar base where the astronauts lived in it for a certain period of time, grew their own food, recycled their water, and simulated the kind of living environment that they might be able to create on the moon. They also announced a Mars program, and the Chinese plan to send a probe to Mars by 2020 and a sample return mission from Mars by 2030. So, and then and there was one more really wonderful quote from Ouyang Zhuan. He added about the Mars program. He said on June 24th of this year, he was asked about the Mars program. And he said, China's goal for space exploration is the solar system. And he then added that another goal of the Mars mission is to detect solar systems beyond Earth's reach and to compare the origins of Earth-like planets with the formation of the solar system. So,
They need more real estate.
They need more.
They're looking for more real estate.
So I know that was a quick overview. We are going to have the basement team I work with. We're going to have a forthcoming article exactly on this, on China's program. But China is totally committed to this, and this is the point Mr. LaRouche makes. People have all these criticisms of China. He said, so what? They're committed to all of their people, and this is their prospect. And they've committed to something which is achievable, and it's defining the forefront of human progress out into the solar system at the highest conceivable energy flux densities and powers. And that is what we must ensure that sets the standard for this new economic system. And then I think just the point I'll end with is that the United States must join this. We must join this. It means our survival, but the United States also has a lot to offer. All these fusion scientists that are left, the people that have worked on these projects, right, they're scattered. They're alive, many of them are alive. They're scattered, they want to do work. Actually, many of them travel to China throughout the year because they can do work there, but they want to do work. And so the United States, we will bring a lot to this thing. We're the premier, we had the premier fusion program in the world.
I mentioned the Princeton because they stopped, they can no longer do anything, and we saw a tour last year, we went there,
Yeah.
the Princeton laboratories.
Yeah, they have a
So,
stellarator.
yeah.
Yeah, they have a stellarator which is in 3 parts, which is a totally,
They
it's the
can't
most
finish it.
advanced stellarator in the world. It's in 3 parts, and they won't give them the money to put
To
it
finish
together. And so the Chinese offered to buy it. They offered to buy it because they want to use
They
it.
want to use it.
And Princeton said, well, give us a little more time.
Well, that's good for the money, we'll do it. Why not?
It's something paltry. It's about like $100,000 or $300,000. Okay, whatever. It's still not that much money.
Compared to what they gave us.
Yeah.
Yes.
500 million.
Yes, let's get questions. Yeah, Marcel.
First of all, I want to say thank you. This is very informative, and it definitely gives us a very strong perspective. The present and what we are fighting for. I wanted to ask a question going back a little bit, because I used to just look into a bit of this, and sometimes obviously with mainstream media, even back in the late 80s, you're not sure what you're getting, what's true, what's not. There were a lot of articles up to 1989 about cold fusion. I believe Pons and Fleischman, Utah and Colorado, and supposedly when they had achieved at supposedly, I guess, cold fusion, room temperature fusion, they had achieved some kind of reaction. Not that they were clear what it was, but that there was some process that was going on, similar, parallel to what you're talking about here. The whole thing was shut down, and we heard nothing else of it. I'm wondering if you know anything about that.
Basically what you know, no, I personally haven't done a lot of work looking into it, but what I do know, and what you're referring to, is that the theoretical assumption, is based on theorized knowledge of the properties of plasmas and what kinds of energy it would take to cause elements to fuse together, to overcome the natural tendency to repel and to actually come together. There are certain assumptions about the amount of force that would take, the amount of temperature it would have to be at, the kind of density, how many particles per cubic centimeter you'd have to have. And so the calculations led to the idea that you have to have temperatures over 60 million degrees for deuterium tritium fusion. And as you're referring to, in the 80s, you had these experiments at MIT where you had a completely different idea of the approach to fusion, rather than what could be considered a certain brute force approach with these machines. You had the idea of, and this is, again, I cannot explain it beyond what I'm about to say, but you had the idea of using a certain certain crystal lattice structure to actually somehow affect the fuel and cause fusion. That was the idea. Now what happened is they ran the experiment, they got neutrons. They detected neutrons coming out of the experiment, which indicates there's some fusion process happening, or something's happening. And they did not want to release their results, because they wanted to repeat the experiments, figure out what was going on, and have a more solid hypothesis to offer. But there was an intervention because somebody wanted to shut the thing down. And so they were forced to publish their paper right away, and then this elicited total hysteria from the fusion community. This is impossible, you guys are witch doctors, you didn't do what you said you did. Basically killing that. And now, like today, people who do research on this, it's not called cold fusion anymore. It's called like low energy something fusion reactions. Or they had to give it a different name. So anyway, it's definitely a good question. I just don't know too much about it.
I gotta just tell you this. I'm one of the people who was selling those fusion magazines. And I'm probably in that picture with McCormick too. I don't know whether I was right behind him.
So all your questions about the FEF.
Yeah. So I was going to make a point, which is that, people were obviously signing up and joining the Fusion Energy Foundation. People were very excited about the whole idea and enthusiastic, the population in general. And the problem was this whole question of budget, right? And people were brainwashed into this idea that it's all about money. You have to cut budgets. You can't spend money that you don't have, something like that. And that was the real fight. And although obviously we're winning the fight with the support of the population, the problem was this ideology about money was dominant, right? And it's come to the end of the road on that, right?
Yeah, that's an important point, that it has been this dominating paradigm of the money system.
And this was the weakness of Reagan, because he basically believed in this idea of budget cuts and balanced budgets and all that stuff. He had the brains to think we should stop nuclear war, which is why he went with the SDI, but he didn't understand the economics of it at all.
Yeah, right, and then that's the fight today, is the population has been so brainwashed and such pessimism has been induced into people. That's why the knee-jerk reaction today is, oh, well, that's great, but you're never going to do it. It's because of things like this, right? Things like what was done to the fusion program.
Isn't that what the credit bank is all about?
Yeah.
What?
Credit bank, because anything that's worth doing, there's never enough money to do anything that's worth doing.
Yeah, right.
And they never will.
Yep. That's exactly it. And that's what we're just thinking about value, right? Is you actually assess value by the revolutionary effect on the productive powers of labor. And then you assess value, assess value from the fact that you can ensure a certain, order of magnitude increase in the productive
And
powers of
increase
labor.
at all times.
Yeah, right, and then currencies, so what do the
The
currency
future.
mean? Yeah, exactly.
Excuse me, it took me,
Oh.
over about 60 years or more, just to get some inkling now of things. But, in the late 50s, there was a advertisement from Swai for free class at the Henry George School. And it was on social science, and I think I learned some, I thought it was a way to get along with girls and so on. So I enrolled in this stuff. I did, it's the truth. I didn't have any college, but I went. And they moved since from their location. I think it was 60th Street, not another place. And when I went to the class, I was sitting down, and the professor was there talking, and he said, "This is all about political science." So I raised my hand and says, "Oh, I must be in the wrong class." So he says, "Why?" Because I thought this is social science, it's the same thing. Keep my mouth shut. And I stayed, and I learned a lot. Progress and Poverty by Henry George. He was very anti-Malthusian, and I didn't know a thing about anything else. But I found it very interesting because I thought along these lines. And I remember that LaRouche wrote a book called There Are No Limits to Growth.
Yep.
And at that time, when I told somebody who had some college, a lot of college actually, and I was mentioning Henry George, he says, "Oh, he didn't take into effect technology." And I couldn't answer him, but I'm beginning to realize a lot of things now. Because he says, well, you had the agricultural revolution, the industrial revolution. The industrial revolution is over. You know, and so on. And now it's not over. You go on and on and
Yeah.
on and on.
No, I'm thinking about Malthus. Remember, that's what Henry Carey said. Henry Carey made, in the quote I read, made this polemic against Malthus. Malthus said that population grows exponentially and food grows arithmetically, right? So the increase in population is going to outpace food, right?
Okay.
Carey said, people make food come from the land, right? The growth of food outpaces the growth of population, but it's just this polemic, right? Yeah. Did you have a question?
Yes, can you explain why Eli and I had an argument a couple of months ago, and he says nuclear power plants are perfectly safe. Can you
Yep.
explain to us why they're safe?
Well, how are they unsafe?
Because Fukushima, Indian Point, Chernobyl, didn't people get radiation poisoning from those accidents?
Who? I mean, just in terms of like Fukushima, for
I haven't interviewed anybody, but
Yeah.
you are from the basement team. maybe
Yeah,
you
yeah.
can
There's, there's a lot of propaganda around this stuff. Nobody died from the Fukushima nuclear reactor. You know, a lot of people died from the tsunami, right? But the
Nobody-
media propaganda doesn't zone in on that. They zone in on the hysteria around the nuclear reactor, which
Just
actually
when it blew up,
performed.
there was no radiation emitted,
No, it performed very well.
so all those villages near Fukushima that we evacuated, the only reason we evacuated was because of the tsunami
Flooding.
destroyed the cities.
And caution, yeah, but nobody has died. Nobody's gotten sick from radiation poisoning from the Fukushima accident. And I mean, this is the thing. Nuclear power plants are very safe. Diane referenced this boat, right? They're very safe. I mean, right? We know how to deal with this stuff. Radiation is actually, we know how to control radiation. These things are very safe. There's hysteria around this to make people scared of these kinds of technologies, like all this business about nuclear waste. Guess what? If it wasn't signed into law by Carter that we couldn't reprocess it, we could reuse 90-something% of the spent nuclear fuel, right? It's not waste, right? It's fuel for the next cycle. So there's just a lot of propaganda that's been put out there, and the population has been bludgeoned with the idea that nuclear power is unsafe to create exactly this kind of drawback
Okay, so
from
the
people
waste
fighting for it.
products that were on the Fukushima site, that they claim were sitting around in barrels, floating away, or leaked or something, all that's not true. There's not, if I went to, a nuclear power plant today and put my hand in and stuff, I wouldn't get radiation.
Well, they're not gonna let you stick your hand down in the fuel rods, right? The point is we have safety measures. We know how to, that's why I said we know how to control it, right? They're not gonna let you stick your hand in and touch the
I'm
fuel
really
rods.
talking about, I'm just being facetious, but what about
Yeah.
the waste products?
Well, that's what I said, is we know how to contain them and we know how to
They're not
reprocess them.
contained properly. They claim that not contained properly. And so the stuff leaked out all over the countryside. Is that false too?
Well, where are the sick people? They actually just released an article a couple of weeks ago.
I mean, it's not useful
Yeah.
to keep asking
Maybe
me a
not
critical
in-
question.
maybe
I don't know
not
if you've ever been to
in
Japan.
long-term sickness.
No, I mean, this, like I said, this stuff is put out to scare people. And there's no
There's
danger.
no such thing as radiation poisoning. There's no such thing as
There is such a
radiation
thing as it,
sickness.
but the point is a nuclear power plant's not gonna give you radiation poisoning because we actually know how to treat these things safely. They're under our control.
Well, the
That's
people
the
on the
point.
news said that the Fukushima plant was out of date and they had not been using the most up-to-date plants and renewable plants are safer.
The newer plants are safer for sure. Yeah,
Okay,
the newer
so
designs are
the
safer
other
for sure.
ones are less safe.
Relatively
Okay,
speaking, but they're still
You're
safe.
just gonna keep telling me this propaganda, so where can I go to find out?
What, Giselle, one thing you should think about is we've had a nuclear navy, a nuclear submarine force since the 1950s. These sailors are on these submarines for sometimes months at a time.
Right.
And they have children and families, and they don't come out looking weird.
Well, speaking of soldiers and sailors, a lot of Iraqi soldiers were exposed
That's
to
different, that's weapons, that's weapons. Weapons are dangerous. Weapons shouldn't be used, we shouldn't have wars. But the power plants are not weapons.
Go on 21st Century Science and Technology,
You
that's
wanna
our
say something?
science publication, and just type in radiation fears or something, you're gonna find tons of stuff. We really go through this stuff in depth.
Yeah, there's a lot more. Anyway, I just wanted to